Polyacrylamide gel electrophoresis, PAGE, describes a technique widely used in biochemistry, forensics, genetics, molecular biology, and biotechnology to separate biological macromolecules, usually proteins or nucleic acids, according to their electrophoretic mobility. Mobility is a function of length, conformation, and charge of the molecule. As with all forms of gel electrophoresis, molecules may be run in their native state, preserving the molecule's higher order structure, or a chemical denaturant may be added to remove this structure and turn the molecule into an unstructured linear chain whose mobility depends only on its length and mass to charge ratio. For nucleic acids, urea is the most commonly used denaturant. For proteins, sodium dodecyl sulfate, SDS, is an anionic detergent applied to protein samples to linearize proteins and to impart a negative charge to linearized proteins. This procedure is called Sds Page. In most proteins, the binding of SDS to the polypeptide chain imparts an even distribution of charge per unit mass, thereby resulting in a fractionation of approximate size during electrophoresis. Let's demonstrate. Brent and Jacob represent two subunits within a single protein. First, we coat them with SDS.
Just made me look fat.
Next, we place them into the wells of the gel. Next, we apply a charge to the gel. Since Brent and Jacob are coated in a negative charge, they will migrate towards the positive terminal. They seem to be stuck. By checking our molecular markers, we see they are stuck around 300 pounds. Brent and Jacob didn't go very far because they are too bulky to pass through the gel. This trial gives us the mass of the entire protein. Therefore, Jacob and Brent's mass is 300 pounds.
Beta-mercaptoethanol, or BME as it is commonly abbreviated, is the chemical compound with this formula you see here. This molecule is used to reduce disulfide bonds. The disulfide bonds are strong with a typical dissociation energy of 251 kilojoules per mole. However, being about 40% weaker than carbon-to-carbon bonds or carbon-to-hydrogen bonds, the disulfide bond is often a weak link between many subunits of several molecules.
Let's demonstrate. Once again, Jacob and Brent represent two subunits within a protein. First, we coat with SDS. Then, we treat them with BME. Now we will load them into the gel. Once a current is applied, the two subunits will travel through the gel. As you can see, the smaller subunit can move farther now that the big subunit isn't holding him back. This separation based on size is extremely useful for identifying the molecular weight of a subunit and for purification. The molecular weight of our small subunit is just over 100 pounds. The molecular weight for our large subunit is right around 200 pounds. Using the first gel that we ran, we were able to identify the total mass of Brent and Jake's subunits as 300 pounds.
And then once we treated the overall protein with both SDS and beta-mercaptoethanol, we were able to find both Brent and Jake's mass, which had two different subunits. Brent's mass was 200 pounds and Jake's mass was 100 pounds. We know that there must have been a disulfide bond because the beta-mercaptoethanol broke it. So this is what the structure of Brent and Jake would look like connected by the disulfide bonds.
I'm videotaping now so that if you break it, I have evidence.
We're putting these on end for sure.
What are you doing, O'Reilly?
I'm entropy. Deal with it.
Next, we apply a charge to the it's not the well, it's to the gel.
Do whatever for the disulfide bonds. And Jake's recording now because he wants bloopers. Oh, and he
Beta mercaptoethanol, or BME.
Deuce. I thought you were my dimer.
we belong together.
Bye, Dr. Johnson. Thanks for being a part of our video.